In the last video of this week's 101, I will just come back to the problem whether we can see a mapping via a diagonal matrix, which was the optimal version, or what to do with the rotations like things. So let's go for that. Right. Now the next question is, we know that we shall come back to that and prove it in many months, because our tools are not rich enough to be really on the safe side, but we can remember to be told, and we can remember the fact that actually each polynomial over complex numbers has got so many roots as the order is, and there might be multiplicities. And now the point is that you can get two different problems, which we saw both of them with our 2x2 matrices in the very beginning of this short video. The first one is that your matrix has got a characteristic polynomial without, well, actually three problems, right? So the first one is that your characteristic polynomial does not have real roots. Then it would have complex conjugate rules, right? So for example, if the dimension is 3, then always there must be at least one real root, because the complex ones would come adjoint, conjugate to each other. So one of them has to be conjugate to itself, and then it's real, right? That was the rotation, right? So we had two different roots, two different eigenvalues, but they were complex. The other problem is that you have the eigenvalues which are having some multiplicities, but the algebraic multiplicity of the eigenvalue is not the dimension of the eigenspace of vectors. And that was the case of the projection, right? So of the nilpotent thing, because with the nilpotent thing, the matrix B, there we had multiplicity 2, but only one-dimensional eigenspace, and that's the main troublemaker, right? So we shall see how to deal with this in a couple of weeks too, but that's much more complicated then. So what's nice, and that's this theorem, if I happen to have different real eigenvalues, then for all different eigenvalues, the eigenvectors will be linearly independent, right? So the generic case, if you randomly choose your matrix, or you don't do it randomly, but you, let's say, Sage compute it with float reals, then it must happen that there will be simply enough eigenvalues. They will be all different, and if they are at the same time real, then you are done, because you have a basis of eigenvectors, and having basis of eigenvectors is the same thing as having a basis where the matrix of the mapping is diagonal, and that's the nice case C in our beginning, where we believe that we know exactly what the mapping is doing. Very nice, right? So that's here. Right, the next thing is that the mapping might keep some linear subspaces invariant. If it happens, then the invariant subspace W, so this one, is obviously kept by the mapping. So if you remember, if I write down the mapping in a basis which starts with a basis of W and then completes the basis to the whole space, then definitely the images will be again expressed exclusively with these elements of the basis, and therefore the matrix will have this blockwise form. There will be this block of zeros, which is as wide as the dimension of the subspace. But we don't know anything about the C here, right? So the C might be non-zero. Depends how we complete it. If it's possible to find a complementary subspace, then the C will be zero as well. Yeah, so that will be then the case of our matrix C, where we had just the complement were the standard basis, one-dimensional subspaces generated by the standard basis, and the mapping was blockwise diagonal, except it was 2 by 2, so the blocks were just one scalar. But the same thing works in general. Right, here is a typical example, so I can skip that, you can read through yourself. That's very easy going. And now the end of the talk, so I'm sorry this one gets longer than I expected, but it's because there are a bit more things to explain. So let's imagine that we have got two real vector spaces with scalar products. And let's restrict our attention to mappings which preserve the scalar product. So we call them orthogonal mappings. And it can be seen that it's enough to test it just on the norms of U, right? So the norm of the value is the same as the norm of the original vector. Because if you plug it in this way, then you find out that you can compute the rest out of these. So that's easy. If you look at the way how we write it, then it's obvious that the same thing as in the plane will work in the general space as well, because in the coordinates, in the orthonormal coordinates, we know already from the previous discussions this week that at every such space we can find orthonormal base, right? And in the orthonormal base, the scalar product is expressed just like this, and in this orthonormal base, the matrix will so the linear map will act this way. So if we just write it down how it is, it will be this. And you see, from this must be true from all vectors x and y, and therefore you know that the transpose to the matrix A must be exactly the inverse. And that was already what we saw in the plane, but there we computed it in a much more pedestrian way. But this is a very nice thing to know. And moreover, it's easy to see that if you take an invariant subspace with respect to an orthogonal mapping, then its complement, orthogonal complement, is also invariant. It's also invariant, and therefore that's the proposition here. The orthogonal complement is also invariant. And it's a very straightforward computation. You don't have to worry about. Just have a look, and therefore for orthogonal mappings, we can always find the decomposition in some sense to the orthogonal subspaces. And this is a bit more complicated here, but just have a look. We shall come back to that in 2 or 3 weeks anyhow, in more general situations, so we don't have to go through the detail. But the message is that what we saw was the two-dimensional rotation, which was recognized by having the complex eigenvalues there, is true in general. So whenever you have got a real vector space with scalar product and a linear mapping on this space, then the space will always decompose into one-dimensional and two-dimensional subspaces. The two-dimensional subspaces will correspond to rotations. The rotations will always be given by the argument of the complex eigenvalue in its polar form. And if it's a one-dimensional subspace, then the eigenvalue will be 1 or minus 1, because it has to keep the sizes. And that's it, right? So it's actually absolutely explicit and complete information. And particularly if you would be dealing with computer graphics, you are perhaps interested how these things happen in dimension 3, right? And in dimension 3, it's particularly easy because in dimension 3 you simply get your matrix. I will just write it here. Get your matrix A. You check whether A times A transpose is E. If yes, you check it's an orthonormal mapping. It's an orthogonal mapping. But then there will be eigenvalues, and one of them will be real, right? So lambda 1 will be is plus or minus 1 eigenvalue, and there will be a non-zero eigenvector, and this is the axis of rotation. And then there is lambda 2 3, which is x plus iy minus the two complex conjugate ones, and this gives you the angle. And the angle is given by the argument of the complex numbers in the polar form. Here here we have to take care about the orientation, in which direction we rotate. Just you can read in the text how to solve this or crack this. And here the plus minus 1, these ones, they correspond to the fact that if it's plus 1, it just rotates. If it's minus 1, then on top of the rotation you have to consider the reflection with respect to the two-dimensional plane. Right, so it's in R3, so it all makes sense. So, sorry for having it longer than usual, and thanks for your attention in this week. Looking forward to chat.